In this video, we'll look at how we can implement Newton-Raphson for a system of nonlinear equations in MATLAB. After studying this video, you should be able to implement Newton-Raphson for a system of equations. Also, you should be able to formulate the Jacobian matrix using analytical derivatives. And finally, write a function M file to return the Jacobian matrix for each iteration of Newton-Raphson. So first, let's look at an function M file to implement Newton-Raphson for a system of equations. So in this function, we are going to need as inputs, f will be a function that returns a column vector of function evaluations. J is another function that returns the Jacobian matrix for the system evaluated for a column vector of x values. Then xi is going to be our initial guesses, and we have our standard stopping criterion, maximum iterations, and var again, so that we can handle parameters if we need to pass those through to our f and j functions. So now coming down to the iteration, we will start by just assigning xi to xold, and then entering the iteration. We're going to go through and solve for dx. This is just dx is equal to j, and left division, negative f, like we developed in the previous video. Then add dx to xold to get our next guess. Calculate EA, check for convergence, and update our old guess, and continue iterating until we converge and break out, assign x, and now this again will be a vector, column vector of our root estimates. Recall that in Newton-Raphson we're setting this up as a system of roots problems, and I've also set this function up to output the residual, which again is just the function. That'll be a vector of residuals, and that's just the function evaluated at those final root estimates. So now let's look at using this function to solve that example model problem from before. So here's this system of equations, and I derived the Jacobian for the system of equations in the previous video, and over here is the MATLAB function to calculate the Jacobian. So it inputs a column vector of the current guesses of x at the iteration, pre-allocates a 2 by 2 matrix. Since this is a 2 by 2 system, this is really where we are encoding this problem into the system, and then assigning each of those partial derivative expressions to those positions in the Jacobian matrix. So recall this was df1, dx1, df1, dx2, and df2, dx1, and lastly df2, dx2. So there's our function M file to calculate the Jacobian. We also need a function to calculate the function evaluations, and I did that with an anonymous function. So here's our function to calculate the f sub i's for each iteration, our initial guesses, and then our function call to NRSys, which is what I called the M file for implementing Newton-Raphson. One note here, since this Jacobian is a function M file, that's why you'll see a little at right here. That's since J analytical is an M file, and as opposed to F, right? Recall that's called an anonymous function. So that's why there's no at for the f. That's what we've typically been doing in the class so far. But now J analytical, that's complicated enough. We could define that as an anonymous function, but it's getting to the point where it's clearer to do it in an external file. So we did that in an external file, and then MATLAB knows to refer to that external file because of that at. So that tells MATLAB to look outside the workspace. Otherwise, MATLAB's just going to look in the current workspace and look for a variable or a function handle that's defined in the current workspace, and it's going to return an error. And then we have a stopping criterion, epsilon s, and maximum iterations. You can run that in MATLAB. I would encourage you to try out the M files included in the video folder to run this in MATLAB. Maybe step through it in the debugger to see how it works. And let's look at our final output here. So we see our final values of x are 2 and 3, and a residual on the order of 10 to the minus 13. And the error, we did way better than our stopping criterion on that last iteration. Our error is on the order of 10 to the minus 14, our final approximate relative error, and the method converged in 7 iterations. So pretty fast convergence. But then again, this was a 2x2 system. So I'd encourage you to play with this file, maybe see how the convergence behavior changes depending on different initial guesses, and make sure you understand how to implement this on MATLAB.